Hi, welcome back to the lecture series on GPU architectures and programming. And so, in the last lecture, we have just introduced the example on OpenCL and CUDA kernel, if you remember. And we have just shown a simple vector add example where we are side by side showing examples of OpenCL and CUDA kernel just to identify what would be the differences in the way things are to be written when you are creating an OpenCL kernel. So, from this one thing is for sure, we understand that both are kind of extensions of C, and when we come to OpenCL, there are several variants. At the lowest level, you have the OpenCL C specification, which is being implemented in the form of a C library that can execute in a data parallel manner in the suitable devices. And at the high level, you also have C++ based wrappers, and you also have PyOpenCL, which is a higher level wrapper, which makes the job of writing OpenCL kernels far easy, at least writing the host program and specifications far easy. For our purpose, since we are living with a C background in this course, we are assuming only that. So, we are looking into everything at the lowest level, that how OpenCL C library is specified, what are the function calls which are used for different functionalities. So, coming back, if you just recall the way we discussed the different layers through which OpenCL code executes. So, every OpenCL program would comprise this host program that will start with some platform layer level queries because in the runtime system you have the platform layer followed by the runtime. So, these are essentially queries going to the platform layer to let know what are the compute devices available in a system. And again, I would say that this is the way you are going to write a generic code. Of course, if you are going to write a simple OpenCL code which is specific to some device, your code can be much simpler. So, initially you will be querying the compute devices, and based on this query you will get the result of how many different how many compute devices are really there, and what are the different vendors from they come from, which are the what is the organization of the compute device, which of them sit in the same die and all that. And based on this information of compute devices, you can decide that you will be kind of accumulating a set of devices together to define what we call as a context. Essentially, that a context is an abstraction through which multiple devices can share their data. If you have segregated a set of two sets of devices into two different contexts, they would need to communicate among each other through the host program without having any direct scope of communication or synchronization among them. Now, once you have queried the compute devices, understood their organization, and created the context in the platform layer, you move on to the runtime, where you actually, so this is all happening in the simple in one program, right? You have to do all these things followed by execution of the kernel. So, we are just trying to specify the structure of the program here. So, these are the initial structures, and now they will be followed by the way different memory objects are to be created and they are to be associated to the context. So, this is the part of code which should come immediately after you create the context. Once this is done, and and we also assume that you have the kernels being written, and the typical way in which the host program would be managing the kernel, well, this is something really a bit different. So, essentially you will be capturing the kernel like a string, let us say in a character array. So, once that is done, there will be OpenCL commands which will be used to create a program object from that character string which is containing the kernel, and with this you have the entire setup ready. So, just to summarize again, you have queried devices, you have segregated devices belonging to different vendors in an architecture specific way, so that you can create so that is the idea of platforms, right? You may be having different platforms connected together using the platform. In the platform layer, after you query the devices, you create contexts. Now, of course, one context, again this is also important, that in one context typically it would be using that vendor's OpenCL implementation. You may have two different contexts sitting in two different vendor provided devices, two different vendor provided platforms containing multiple devices. So this is very important. You have to understand you can have multiple platforms coming from different vendors, and each platform can contain multiple compute devices of CPU, GPU, maybe some other compute nature like TSP and all that. So that's why all this complexity at the lower level program can come in, but you have to also understand that this gives you a lot of power with respect to deciding how to really program such a heterogeneous device. And as we move on, the importance of heterogeneous devices will be clear very soon. So you query the devices, you understand the entire setup of the system. That is, you understand which are the different vendor supplied devices or platforms. Inside the platforms, how are the devices organized? Based on that, you can have, let's say you have 4 devices in a platform. You can create, I am just giving an example, subsets of 2 devices to create 2 different contexts, or you can bunch in all the 4 devices together to create a single context, and like that, right? And then in the next part here, what we have is the things that you do after the contexts are created across different platforms, right? Or if I am having a very simple architecture, I may be creating context inside a same platform, and then you create data objects associated to the different contexts, and then you create kernel objects based on a kernel specification which is encoded inside a character array, and that is compiled to create the kernel objects. After all this, what you have is you have programs ready as objects, right, which will do the compute, and you have data segments also set up as memory objects, so that are containing the data on which the programs are going to, or the executables are going to compute, right. So what is the logical next step? The next step would be that you have to set up a sequence of commands which are to be executed. What do I mean by commands? Commands means when and how to run which kernel on what memory object, produce the result, write it to which memory object, followed by which kernel's execution, all this stuff. So to give you an example, let's say I want to implement the following computation. I have kernel A and kernel B, they are producing data, and that's going to 2 buffers. Once the data is ready, then I want some kernel C to fire and produce the data and move again to a buffer, right? And you have these input buffers. So I have a sequence of operations, right? So I need to write the data into these buffers, right? This is also important. You need to remember that initially you don't have, you just have these buffers there, right? And you have these kernels available to you as program objects. These are available as memory objects, buffer objects, right? So you need commands to write data here, you need commands to execute these kernels, you need commands who will let you know that these kernels have executed and produced data, and then you need another command to execute this kernel, and again you have to query the system to know that this kernel's execution is done, so the data is ready here, right. So that means I need a sequence of commands somewhere, because if the commands are set up in a wrong way, then everything is going to go wrong, right. So this leads me to the idea of what we call as a command queue, through which all these commands will be sequenced, and that will provide me a specific order in which the operations have to be carried out, so that this required functionality is actually implemented, right. This is very important. So I am just trying to motivate why I need this command queue, this idea of a command queue, because unless I have a queue like structure for storing commands, I don't have any way to force this kind of dependencies and sequences in the execution, right. Of course, I also need something else, right, which is, for example, if I take this thing that this guy is going to execute only when the data is ready here and here, right. So this would be naturally like a synchronization point in the execution, right. So how do I specify which are the points where the programs need to synchronize? That would require not only execution commands, or read or write commands, but also synchronize commands. So in this way, I'm just trying to motivate what are the different kinds of commands that are going to be part of the command queue, right? So once this is done, let's say you get the data ready here, you know that things are done. You need to clean up the resources that you have consumed in the system. That would mean you need to clean up these buffers, you need to clean up these program objects and everything, right? So in what form is essentially a kernel present? As we have said, that finally inside the host program, the kernel has to be available like a string stored in a character type array. In general, when you are specifying the kernel, is just like a normal C code with some restrictions and extensions. I mean, typically there would be some OpenCL constructs which have been pushed in the form of C functions, which are implemented by the runtime. And also you have to understand that this is a data parallel code. So essentially in the C code, what you write is all per thread behavior, just like a CUDA function. So with this, we will first take an example of a host code. So this was our example of a kernel code, and now we will take an example of a host code. So essentially it's just like a normal C program. As you can see, you include stdr.h, std standard library.h, and then you have OpenCL specific declarations in cl.h. So these are the declarations that are kind of specified by the working group, the joint working group called Chronos. So you may visit this website. So this is essentially the joint working group's website, who actually specifies all the standards and specifies all these functions for OpenCL, right? And what will be their behavior and all that. Now, whenever some vendor will conform to this behavior, they will provide the library which will contain the implementation of the functions which realize this behavior, right? So let's just have a look into the program, like what's really going on. So as you can see, the initial part is just like a normal C program. You are declaring three spaces using memory spaces. You are allocating them memory for HA, HB, and HC corresponding to this data size, right? The length of the vectors that you would like to work on. And then let's say we are just using a code to fill up these vectors by randomized initialized values. Once that is done, now comes the platform specific programs, right? So let's have a look at how this platform is created. This is very important. Please pay attention here. This is the point from where things become different from our normal C program running in a desktop computer. So first you see the usage of a OpenCL type here. So you have a CL_uint for OpenCL kind of unsigned integers. So that would be storing the number of platforms. So you are initializing a variable num platforms for storing the number of platforms that would be available in a system, right? So for getting that, you make a call to this function cl_get platform IDs, right? So this is the function which you are calling. Now this is the this is the kind of declaration we have put in the comments here for the function. So as you can see, in this comments, we are specifying that this is asking for the following: the number of entries, and then you are hoping that it will actually give back the entries, and so that would be coming in another output, which is the CLUint type point. This is a pointer to number of platforms, and then also there is another argument. We will soon see why this is useful. So first thing you do is you make a call to cl_get platform IDs with the number of entries, the first parameter set to 0, and the second parameter which is of type platform ID. So that's another OpenCL type for platforms, that's also set to null, and you are just passing the address of this variable, which is a CLU unsigned integer type, which is the num platforms variable, all that is going to happen is, if this call is set up in this way, with the first parameters being 0 and null, it will essentially write the total number of platforms into this variable. That's all that will. Suppose there are only 2 platforms available, this variable will get a value 2. If it's only one platform, it will get a value 1, like that, right? In case it's 0, we have written some handler code that then it will just return back right from here, because it is not able to find, it's finding 0 platforms, right? There are no platforms at all. Now, suppose you have figured out through this call that what is the number of platforms here. Now, you are going to use exactly the same call again to figure out what are the different platforms. Because just knowing what are the platforms are not going to, how many platforms you have is not going to help you, right? You need more information, like how to access each of these platforms. For that, you again make a call to the same function. You can see the functions are same, CL get platform IDs, but the arguments are different. Initially, you give the first argument as 0 because you simply didn't know. So that's like an initial value you are giving, right? But now you know how many platforms are there through this style of call to the function. Now you are calling it in a different style. You are supplying it the value of number of platforms, right? And you are setting up something here, which is you are passing it a variable which would be platform, and its type is CL platform ID, right? So of course that needs to be declared here, and that's something you have to do. So suppose you have this, so you have earlier it was set to null. Suppose you have already declared this, that what is CL platform ID, and then you have given this variable's name. This is essentially a pointer here, and you are now setting the last thing to null, because now you want this function to act in a different way, because you already know how many platforms are here, but you really want to copy back these platforms IDs to some structure which is of type CL platform ID. We have been declaring it here. So you have CL platform ID type for this variable platform, which is essentially an array, and by knowing a proper initialized value of num platforms, you are able to now declare. So this is like a dynamic array you are declaring. You are able to declare what should be the size of the platform array, and you are using that size which is now known to you. You are simply declaring platform of size number of platforms, and it's of type platform ID, because you expect this array to contain the num platforms number of platform IDs, right? So you have these many entries. Each of the entries should be a valid platform ID. So when this call will be set up in this way, and it will, if it returns without any error, then this platform array will get filled up with all the all the IDs of the platforms in each of these positions, right? So you can see that you are using CL get platform IDs to first recover the number of platforms that are there. Accordingly, you are declaring the dynamic array, and then you are populating that array in different each of the positions in the array with the platform IDs which are being recovered using the second call. Now let's inspect this code very minutely. This has been written in this way just to give you a general feel how things occur there. So you know now what are the platforms using their IDs, right? But as we know that in OpenCL we are assuming that the underlying system is very complex, like there are things from multiple different vendors, and each of these platforms may contain multiple devices like one CPU, one GPU, or multiple GPUs, multiple CPUs in one device, in one platform, and again in another platform multiple such devices and all that. Till now all that you have got is the platform IDs, right? So now you would like to get the device IDs for each of the platform IDs. For this you are going to use this function CL get device IDs, right? We have provided here the prototype of this function. So it would be taking the following parameters. You are going to ask the system what is the device ID is available for some specific platform. So, the first parameter is of type CL platform ID, where you are going to push the specific entry of this earlier platform array, and then you are also going to provide it with the type of devices that you wanted to discover. Maybe you are interested in only a set of only a specific type of device like CPU or GPU, then this will give you those device IDs, right. And then you also have an entry for CL number of entries. You provide it a pointer of type device ID, which you wanted to figure out and provided the device ID back, and then you have another pointer or number of devices. This is also of type unsigned int, right. Let us see how things get set up. Now that we have identified that what is the number of platforms, so using that, so this is the number of platforms which you have now figured out from this call, and you have declared this and you have filled up this array platform with the different platform IDs. You make the declaration of another 2D array called all devices, right. So, this is of type CL platform ID, this is of type CL device ID. Why is that 2D array? Because for each platform you can have technically multiple devices. So, we are just making a declaration like this. I mean, these are static, there is a reason. So, for each platform we are expecting in the architecture that devices are of two types, right. So, we are writing it 2. Of course, this is not generic, I am just repeating, where we are simply assuming in this case that the devices are only of type CPU and GPU, we make it 2, and we are giving an upper bound on the size here, which is also statically defined. So, for each platform there can be 2 device types, and each type can have multiple devices which would be stored in these positions, right. Now, let us see how the thing works. We are going to browse through querying the system, and for each of the platforms we will query the system for device IDs, and we will get the device IDs. There is a code that we are going to run, and this is how it works. So, we have a for loop through which will run from I equal to 0 up to the number of it will iterate for number of platforms types, right. Each of the values of the iteration, what is going to do is, so suppose you are iterating for 0. So, so essentially you have got the first platform ID at platforms 0 position of the array, right. So, now you fire this CL get device IDs call. Using this call, you have also provided it with, let us say, platform 0. So, the first entry with the platform ID in this array. For this platform you are trying to discover devices of type GPU, right, and here you also pass it with the num devices, which has been declared right here immediately before the call. So, in every iteration you will get a fresh variable here called num devices, right. So, with so this will give you back the number of GPU devices that are available in platform 0. I am speaking of things going on in the I equal to 0th iteration, right. So, with this call, so as you can see the structure is again similar. You have the same call, same kind of call made twice. First you kind of discover what is the number of GPU devices that you have in this platform, and then you make the second call again with num devices initialized. So, it looks similar platform, right, and then so just pardon us, we have this being inconsistent, like this is platform, and so this should mean, let me make the correction right here. So, platforms I, whereas the issue is, as you can see, we have here declared platform with p caps. So, let us just follow that here, and I believe you should be able to resolve it. This is fine, right. So, with this first call we get the number of GPU devices in platform, in the first platform, then we provide that value here, and we are expecting that this system, earlier as you can see that two of these arguments were 0 and null. Now we are actually setting them up. The first argument, because I am initializing the number of devices to 0, now I know the number of devices, so I put it here, and then I want those device IDs to be returned, right. So since my query is what are the number of the devices of type GPU in platform 0, now I know that. Now I want to know that what should be what are the device IDs for those GPU type devices in platform 0. So essentially here I am providing it the pointer to all devices num platforms. In place of 2 I will have 0. Let us say the first part is for storing the GPU IDs, and then so that would be the pointer, right. And so I would expect with this call this array would get populated with the different GPU ID device IDs for platform with ID 0, right. Now in the next again I will just repeat the same thing. So again you are firing the get device IDs call, right. Using this get device IDs call you are figuring out what are the different, I mean how many GPU CPU type devices are there in these platforms, how many CPU type devices are there in this platform. You are essentially figuring in platform 0, right. And then for all those devices you are storing back their device IDs, right. Inside this all devices num platforms CPU for CPU you will use this, you will have 1 here, and all the rest of the positions in that array will be filled up with the CPU device IDs, right. As you can see that this is a 2D, this is a 3D array. So if I am access it at 2D level, essentially I have a pointer, right. And since I have passed it, the function will write back inside this array sequentially in these positions like num platforms 1 0, num platforms 1 1. In all these positions it is going to write back the CPU device IDs for platform 0, right. So with this iteration of this loop I have discovered as it iterates through all the platforms, it have discovered all for each platform device IDs for CPUs, device IDs for GPUs and all that together, right. For this example we have chosen the first device to be a GPU device in the first platform, right. So maybe with this part we will be ending this lecture. See you soon. Thank you.